So Reis will tell us about subspace flatness and integral programming.
Thanks, Avi. Yeah, so my research is in convex geometry and discrete math. I understand that a lot of you are not super familiar with the topic. So yeah, so this is some joint work from my advisor Thomas. So I'll be giving some like brief introduction to field. So here, one of the objects of study here will be lattices. Lattices are just discrete subgroups of Rn. What does this mean? It means I give you some bases here, B1, B2, and I take the integer linear combination of these bases, and this is my lattice. The bases need not be unique. Well, here's a notion of determinant is like a measure of like how sparse the lattice is. And it turns out that this is independent of which bases I pick from my lattice. Like the area of these two things are the same. Another interesting thing is that these things, this B of the unit cube, I'll call this a fundamental parallelepiped. It turns out that these things tile the space. For example, here, I can put a copy of this parallelepiped in every point of my lattice, and it turns out that every internal point here is covered exactly once. This is not too hard to see. Essentially, like it's kind of like taking a fractional part of an integer. Like I have any point here, I can like subtract copies until I reach the fundamental parallelepiped. Okay, so another concept I'll be talking about is the covering radius. So I won't talk about lattices. I'll also talk about convex bodies. So here I'm given a lattice spanned by this base B1, B2, and I have some convex body here. And I'll define this covering radius as the least scaling for which if I put this convex body in every point of my lattice, it covers the entire space. It turns out that another equivalent definition is, if I have any center here, it doesn't have to be in the lattice, it's X here. This covering radius, it's the least scaling for which, if I scale this convex body K here, it intersects my lattice. So it may not be obviously clear why these two definitions are equivalent, but it's not too hard to show by using just the symmetry of the lattice and of the space. So the convex body need not be symmetric to the structure. So we don't have a good way of computing this covering radius, but I guess this talk will be talking about like some approximation of this. In particular, I'll be talking about some ways we can find lower bounds, certify lower bounds for this covering radius in terms of the volume of the body and the determinant of the lattice. So here's the only thing I'll prove in this talk is this lemma. It's saying that like if I have some convex body K that covers the entire space, the volume is at least the determinant of the lattice. And this corollary here should be understood that it holds for any convex body in any lattice. It doesn't have to satisfy this part. So okay, I'll give just the proof of this part. It's not too bad, so bear with me for one slide. So the volume we know is the integral of the indicator function of the convex set. And by the previous slide, we saw that we have this tiling, and therefore we can write the space as a union of these fundamental parallelepipeds at the lattice points. And if you look at this sum, what is this? Is this counting how many lattice points are there in the translate of my convex body? And by the assumption that I'm covering the entire space, we know that there's at least one. And therefore, this is at least the volume of my fundamental parallelepiped, which is the determinant of the lattice. So essentially, another way of saying this is that if I have a convex body that covers the entire space, it's sort of like volumetrically it has to be as large as the fundamental parallelepiped. Otherwise, there will be some point that's like not covered. This corollary is also like just a scaling argument. The point is that if I scaled by some quantity that's like below this normalized determinant here, well, what is this number? It's just whatever number I put here for which the volume of this number times K is equal to the determinant of the lattice, which is a normalization factor. And if you have some radius that's like below this quantity, by this lemma, by the contrapositive here, you'd have the covering radius that is greater than 1. And just by scaling K, you get this result here. Okay, so this is a general lower bound on the covering radius for any convex body K and any lattice L. So if this slide was a little confusing, let me show you a picture. So here's a lattice. I have some bases, B1, B2. The determinant is just the area of this parallelepiped. And I have some convex body K. This is an ellipsoid. And okay, maybe I want to put copies of my ellipsoid over everything in the lattice. It looks like this. And here you see there's a lot of overlap, like this, the ellipsoid, like it's kind of like flat in this direction. So it's not covering a lot of the space here. And therefore, so this is the scaling for which this lower bound would give. And you can see that it's very much not tight. There's a lot of space here in this y direction, which is like sparser than the x direction, which is not covered. So I guess this, what I'm trying to say is that this lower bound here can be arbitrarily bad. Like if this ellipsoid was like thinner and thinner, this would be worse and worse. And this is what Kanan and Lovas noted in 1988, and they proposed a different lower bound, which is a slightly more sophisticated. So instead of just looking at the entire space, they said, okay, what if we take this covering and we project onto some direction? So here's the idea. I have some subspace W, in this case, just a line here. And the observation is that, if I have some subspace for which, originally I cover entire space, I can project onto W, and this will still result in a covering of W. Okay, because why is this? Because the projection is a linear map. Okay. So what does this mean? It means I can apply the same lower bound I had before, but restrict it to my subspace W. So let's see in this example here, I had these like a bunch of ellipsoids in this x direction, and kind of like they all collapse to like a line here, it's like a segment. And the lattice is just these points here. They just project to these points. And if you look at this, the determinant here is just the length of the segment. So it turns out that the length of this segment divided by the projection here is a better lower bound than what was given before. Because I'm sort of like, I'm like looking at exactly the direction which is relevant in some way. So what Kanan and Lovas asked back in 1988 is, okay, we have this lower bound for any subspace. The question they asked is, okay, what is the best possible lower bound I can get for your favorite subspace? So what they end up showing back then in 88 is that if I have a convex body and a lattice and I define my covering radius, there's always some subspace W for which this lower bound I showed in the previous slide is tight up to a factor of n. So this is for any convex body, any lattice. I can always get an approximation that depends only on the dimension. Okay. And in his thesis 10 years ago, Daniel Dadouche asked whether we can replace this n here by a logarithm, this log of n. And I guess what we showed this year is that we can in fact get this up to a log cubed of n. And so this is a result that used to be known only for when the convex body K is an ellipsoid. This proof is already fairly complicated. So this is the work of Dadouche and Regev back in 2016. What they showed was that if a form of like a reverse Minkowski theorem is true, then this holds for ellipsoids. And the next year, Regev and his PhD student Steven Zavidowitz, they showed this reverse Minkowski theorem, which I don't have time to explain. It's a paper in Annals of Mathematics this year, so it's kind of hopeless to do that in 15 minutes. And I guess you could ask, okay, why do we care about this covering radius approximations? Computer science, one reason is that Dadouche also showed that it implies this faster algorithm for integer programming. So this problem is the following. I give you as input a convex body K, and the problem asks, can you tell me whether this convex body contains an integer point or not? And if so, give me some integer point. So Dadouche in his thesis and also in the follow-up work in 2019 laid a lot of groundwork that essentially we could just port and transform this theorem into an algorithm for integer programming and time log n to the order n. So I don't have a lot of time to explain the entire proof of this theorem. What I choose to do instead is I'll just give some flavor of convex geometry. So far I talked about lattices. The missing piece here is talking about these convex bodies. So I'll just briefly try to explain. So here we used to know that it's known for ellipsoids. So I guess the starting point of our work is, okay, we know it's for ellipsoids. How can we make a body look like an ellipsoid? So it turns out that there's a classical theorem of John, 1948. It tells you that any convex body can be approximated by a unit ball up to a linear transformation with a factor of n. And the factor of n is tight in this case. That's because if you take a simplex, it's not too hard to see if it's a regular simplex, the circumradius and the inradius have a ratio of n. So you can't really hope to beat that. However, the insight of a few geometers of the 70s is that we can relax this notion of containment, which is very strict, to like an average containment notion, which I'll try to articulate a bit hand-wavily. So I guess here's an example. Here I have this unit cube, and here there's a circle here, and there's another big circle. They're squared n apart. As in an image, there's unit balls. Here I drew the polar body of the cube, which is a one ball. If you don't know what the polar body is, don't worry too much. It's essentially like I'm translating these vertices to inequalities, but yeah, don't worry too much about that. So the insight of the geometry is that, okay, if I take a Gaussian random variable in the space, there's another way you can kind of approximate this unit ball by computing the product of the expectations of the Gaussian with respect to the body and of the polar. For example, in this case, it turns out that the expected maximum coordinate of a Gaussian is order squared log n. It's not too hard to show a sure enough bound. And also the expected one norm is order n. That's easy to see by linearity of expectation. Therefore, this product, which is the so-called LL star product, in this case, is at most n times the squared factor, squared log factor. And in the unit ball case, it's order n. So essentially, you can see here that I'm off by a logarithmic factor, which is good. And it turns out that they prove that in general, this is possible. For any convex body K, I can always put in this like average, well-rounded position. Okay, so I'll give like one slide, giving a very high level idea of like why this is, I guess, how we use this in the proof. So we have like 3 logs here. So I'll briefly give a one sentence about what each log means. So the first log, I just make the convex body well-rounded by the previous slide. There's another log coming from this reverse Minkowski theorem, which I'm not explaining to you, to related to lattices. There's a third log from the argument, which is that we have to apply some triangle inequality for the covering radius of the lattice and the convex body, and we need to recurse on the projection, so that takes a log many iterations. Yeah, this is probably, I lost everyone in this slide, but I just wanted to give a high-level idea. And kind of like a story to think about this is this classical story where you have 3 logs, and at least one of them cannot be removed. We know that there's when K is a simplex, we know that there is at least a log factor here. So some of these logs built out of brick. And I guess I have one more slide here, just trying to give a context about this integer programming problem that this implies. So here the problem is that I have a convex body K, and the task is to either find a point inside it or certify that it's empty. In this case, it's empty. This is a problem that well studied. So it's known to be NP hard since the 70s. One of the first problems shown to be NP hard. There's an algorithm that runs in time log 2 to the n squared to Lenstra. That was the first algorithm that ran in time only proportional to the dimension here. Ever since Kanan improved this to n to the order n a few years later, and Daniel Dadouche and my advisor and his advisor showed, I guess, order n to the n algorithms. Like I guess here is just improving this exponent, constant exponent here. And I guess like following the work of the douche, we can get this log n to the order n algorithm. And so if someone is interested, I have another slide to talk about the algorithm. Otherwise, thanks.